Okay, now we'll look at another question that was also from exam 2. Um, Here we're trying to obey the off-ball principle, Hund's rule, and the Pauli exclusion principle to answer these questions. So there's one here. It says a complete electron configuration for a neutral atom of selenium and its corresponding orbital diagram. This would be a periodic table and an off-ball diagram question. The element selenium is right here. It's in the P block, and it is in the fourth. So if you look at that, so it says 1, 2, 3, 4. It's going to end up being 4p4. So where the end is. So this block, this particular elemental block, is 4p4. So it's, again, fourth period, P block, fourth element over 1, 2, 3, 4. But the complete means that we have, got to write everything in according to our off-ball rule. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Then remember, when you go, now you're looking at from after 4s, you're going into the D block, but you got to subtract 1 from that n for that. So it goes back to 3D, but you got to fill it all the way up, so that's 3D10. Then you're back to 4P4, just like that. And you should be able to add all of these numbers across the top here. 6 and 4 is 10, 20, 34. So this should be element number 34 if it's neutral. 34 electrons to go with this 34 protons. So you look back over here, and I've already marked a little bit through there, but you can see that selenium is element number 34. So that part's good. The orbital diagram is going to be your, putting in how the electrons fill up. And remember that the arrows represent electrons. In the first part here, 1s. So this first little block represents an S. So 1 is for S, and each little one can have 2 electrons in it. So the S's have 1 block like this, and the P's will have 3 because you have 6, and the D's will have 5 because you can have up to 10 electrons. So we need to draw this out. So there's your first 2 electrons for 1s, and then giving them opposite spins that way is very important also. That's your Pauli exclusion principle. 2p6, following Hund's rule as you fill those up, and then Pauli exclusion as you spin them opposite. So you see now I'm filling up the second. This is right here is 2p, this is 3p. Now I'm at 4s, so this is a 4s. And then 3d, I got to fill all of them up. So now obviously, if you do this correctly, I'm going to have no way of knowing if you followed Pauli exclusion principle when you filled them up. But just remember, if you're going to fill all of them up like that, that you be sure that they spin opposite. So it doesn't matter to me if you go up, down, whatever. Now when you get to 4p4, that's where we're at now. This is the 4p. This is where it'll be particularly important. Make sure that you put the first 3 electrons in their own seat, Hund's rule, and then you'll come back and do the 4th electron right there. So if you were to put 1, 2, 3, 4 and nothing in this block over here, then you're going to miss it. So Pauli exclusion principle, opposite spin, but the Hund's rule is the bus seat rule, where you put 1 in each orbital before you double up. And the next part says the noble gas electron configuration for lead. So plumbum, right? So when you go and you look at your periodic table, you'll see that lead is also in the P block, but now it is here is your last noble gas that was completely filled, xenon, here, right? So then you can start filling up the rest. So if you look 1, 2, 3, 4, 5, in 5p6 there's xenon. So you can abbreviate here by putting in brackets the symbol for that noble gas. And remember, that's 5p6. So then that would be followed by 6s2. So you look at your periodic table. So you go here, right? And then you go here. Now you have to go through this block here. This is an F block. Now that you have to get. It's right in here. It's not. It's really would have been at the bottom if I'd have copied the whole periodic table. But you really have a 4F that you've got to fill up right there. So remember that an F block can hold 14 electrons, 7 orbitals. So when you write that in, you have 6s2, 4f14, then 5d10, then you're back to 6p, and then you just see which one lead is, and it's the second one. See, this is a first, so this is 6p2. So you can add up the electrons just to make sure. Xenon right here from your periodic table, when you look at it, right, it's number 54, so that's 54 electrons that you have. 54, 56, 70, 82. So the 82 electrons should be what lead has, and it is. It's 82. So just make sure all of your electrons are accounted for based on what you were asked to provide. Next you have a sulfide ion. Now this is not the sulfur atom, this is sulfide ion. So the sulfide ion comes when sulfur gains 2 electrons to look like a noble gas configuration. So you're going to really draw the electron configuration for argon, right? Because that's what it's going to appear electron-wise, what it's going to appear like once it becomes a sulfide. So it's got, right here it's got equal numbers of protons and electrons. But when it has the sulfide ion, it's going to have actually 18 electrons that you're going to draw. So it's going to look like a noble gas, but I don't want you just to draw argon as a noble gas. I want the complete. So here's sulfur, sulfide, so it's going to be 3p6. So the sulfide ion ends in 3p6. So you just have 1s2, 2s2, 2p6, 3s2, and 3p6. And remember, you do get to use your off-ball diagram when you take your test, so make sure you have that available, and it lets you, helps you figure out how to fill up the orbitals as you go through. I will not ask you for one that's weird or in violation of any of the rules of the off-ball principle or anything like that. So there will be very doable questions related to electron configurations, orbital diagrams, stuff like that.